Example 3. A town's population has been growing linearly. In 2004, the population was 6,200. By 2009, the population had grown to 8,100. If this trend continues, A, predict the population in 2013. B, when will the population reach 15,000? The two changing quantities are the population and time. While we could use the actual year value as the input quantity, doing so tends to lead to very ugly equations since the vertical intercept would correspond to the year 0 more than 2,000 years ago. To make things a little nicer and to make our lives easier too, we will define our input as years since 2004. Input, T, years since 2004. Output, P of T, the town's population. The problem gives us two input-output pairs. Converting them to match our defined variables, the year 2004 would correspond to T equals 0, giving the point 0, 6,200. Notice that through our clever choice of variable definition, we have given ourselves the vertical intercept of the function. The year 2009 would correspond to T equals 5, giving the point 5, 8,100. To predict the population in 2013, T equals 9, we would need an equation for the population. Likewise, to find the population would reach 15,000, we would need to solve for the input that would provide an output of 15,000. Either way, we need an equation to find it. We start by calculating the rate of change. M equals 8,100 minus 6,200 divided by 5 minus 0 equals 1,900 divided by 5 equals 380 people per year. Since we already know the vertical intercept of the line, we can immediately write the equation P of T equals 6,200 plus 380T. To predict the population in 2013, we evaluate our function at T equals 9. P of 9 equals 6,200 plus 380 times 9 equals 9,620. If the trend continues, our model predicts a population of 9,620 in 2013. To find when the population will reach 15,000, we can set P of T equals 15,000 and solve for T. 15,000 equals 6,200 plus 380T. 8,800 equals 380T. T is approximately 23.158. Our model predicts the population will reach 15,000 in a little more than 23 years after 2004, or somewhere around the year 2027. Example 4. Anna and Emmanuel start at the same intersection. Anna walks east at 4 miles per hour while Emmanuel walks south at 3 miles per hour. They are communicating with a two-way radio with a range of 2 miles. How long after they start walking will they fall out of radio contact? In essence, we can partially answer this question by saying they will fall out of radio contact when they are 2 miles apart, which leads us to ask a new question. How will it take them to be 2 miles apart? In this problem, our changing quantities are time and the two people's positions, but ultimately we need to know how long it will take for them to be 2 miles apart. We can see that time will be our input variable, so we'll define input, T, time in hours. Since it is not obvious to define our output variables, we'll start by drawing a picture. Because of the complexity of this question, it may be helpful to introduce some intermediary variables. These are quantities that we aren't directly interested in, but seem important to the problem. For this problem, Anna's and Emmanuel's distances from the starting point seem important. To notate these, we are going to define a coordinate system, putting the starting point at the intersection where they both started. Then we're going to introduce a variable, A, to represent Anna's position and define it to be a measurement from the starting point in the eastward direction. Likewise, we'll introduce a variable E to represent Emmanuel's position measured from the starting point in the southward direction. Note that in defining the coordinate system, we specified both the origin or starting point of the measurement, as well as the direction of measure. While we're at it, we'll define a third variable, D, to be the measurement of the distance between Anna and Emmanuel. Showing the variables on the picture is often helpful. Looking at the variables on the picture, we remember we need to know how long it takes for D, the distance between them, to equal 2 miles. Seeing this picture, we remember that in order to find the distance between the two, we can use the Pythagorean Theorem, a property of right triangles. From here, we can now look back at the problem for relevant information. Anna is walking 4 miles per hour and Emmanuel is walking 3 miles per hour, which are rates of change. Using those, we can write formulas for the distance each has walked. They both start at the same intersection, and so when t equals 0, the distance traveled by each person should also be 0. So given the rate for each and the initial value for each, we get a of t equals 4t, e of t equals 3t. Using the Pythagorean theorem, we get d of t squared equals a of t squared plus e of t squared. Substitute in the function formulas. D of t squared equals 4t squared plus 3t squared equals 16t squared plus 9t squared equals 25t squared. Solve for d of t using the square root. D of t equals plus or minus square root of 25t squared equals plus or minus 5 absolute value of t. Since in this scenario we are only considering positive values of t and our distance d of t will always be positive, we can simplify this answer to d of t equals 5t. Interestingly, the distance between them is also a linear function. Using it, we can now answer the question of when the distance between them will reach 2 miles. D of t equals 2, 5t equals 2, t equals 2 divided by 5 equals 0.4. They will fall out of radio contact in 0.4 hours or 24 minutes. Example 5. There is currently a straight road leading from the town of Westboro to a town 30 miles east and 10 miles north. Partway down this road, it junctions with the second road, perpendicular to the first, leading to the town of Eastboro. If the town of Eastboro is located 20 miles directly east of the town of Westboro, how far is the road junction from Westboro? It might help here to draw a picture of the situation. It would then be helpful to introduce a coordinate system. While we could place the origin anywhere, placing it at Westboro seems convenient. This puts the other town at coordinates 30, 10, and Eastboro at 20, 0. Using this point along with the origin, we can find the slope of the line from Westboro to the other town. M equals 10 minus 0 divided by 30 minus 0 equals 1/3. This gives the equation of the road from Westboro to the other town to be W of x equals 1/3 x. From this, we can determine the perpendicular road to Eastboro will have slope m equals -3. Since the town of Eastboro is at the point 20, 0, we can find the equation e of x equals -3x plus b, plug in the point 20, 0, 0 equals -3 times 20 plus b equals 60, e of x equals -3x plus 60. We can now find the coordinates of the junction of the roads by finding the intersection of these lines, setting them equal. 1/3 x equals -3x plus 60. 10 divided by 3x equals 60. 10x equals 180. X equals 18. Substituting this back into w of x, Y equals W of 18 equals 1/3 times 18 equals 6. The roads intersect at the point 18, 6. Using the distance formula, we can now find the distance from Westboro to the junction. Distance equals the square root, 18 minus 0 squared plus 6 minus 0 squared, approximately 18.934 miles.